All right, guys, so we'll continue with our trig unit here. Starting out with a little review first. Given the right triangle there, see if we can figure out the value of the sine of the angle theta, the cosine of the angle theta, and then what the actual theta value is. So pause the video for a second, see if you remember that stuff, SOHCAHTOA, that kind of thing, and see if we remember. All right, so let's see how that went. So again, if we need the sine of the angle, again, we don't know what the angle measure is, and we don't really need it yet, right? Sine just means opposite over hypotenuse. So in this triangle here, based on where that theta, that angle is set up, the opposite side is the 5. The hypotenuse is 13 because it's across from the right angle, so that would make this top side be the adjacent. But for sine, we just need opposite over hypotenuse. Okay, so 5 over 13. Now for cosine, we do need adjacent over hypotenuse, right? So what is the adjacent length, I guess, is the question. And remember, you can always use Pythagorean theorem in a right triangle. So we could say something like the 5 squared plus the adjacent leg, or you could call that b, a squared plus b squared must equal the hypotenuse squared. And if we solve that out, 25 plus something squared equals 13 squared is 169. We subtract the 25 from both sides and get adjacent squared equals 144. Right, and then the taking the square root, the adjacent is going to equal 12. So now I know the cosine of the angle. If the adjacent side length is 12, the cosine of the angle is just the adjacent side over the hypotenuse. Okay, and then to actually find theta, find the what is the measure of that angle, you could use either one of these. And what we could do is we know that theta would equal, let's just say I use the answer to part A. Remember to solve, like if you want to solve that equation for theta, you need to do the inverse trig function. So the inverse sine of 5 divided by 13, and if you have a calculator, definitely going to need one. In degree mode, right, just like we did the other day, we're going to get an answer of around 22.6 degrees. Okay, or another option you could have done using the answer to part B, we could have done the inverse cosine of 12/13. So now we get to the exact same answer. Okay, all this stuff really is related to each other. There's a lot of relationships and things like that. You could also have done one other thing with tangent. You could have done opposite over adjacent, 5 over 12, done an inverse tangent of that, and got the exact same answer again. Okay, so that was just a quick little recap. So SOHCAHTOA and calculator stuff. Let's talk about now opening things up. Okay, you can get angles. If you think about a triangle can only have 180 degrees total, right? Or it must have 180 degrees with all the angles added together. So you are not able to get angles bigger than 180 in a triangle. You're also not able to have negative angles. Okay, but both of those things are possible in trig. Okay, so instead of just dealing with triangles all the time and right triangles, we're going to actually extend it to circles. Okay, because in a circle you have 360 degrees, and the crazy thing is you can even go around as many times as you need to. You could go, 720 degrees would just be 2 full circles, so it would actually end up in the same spot as a 360 degree angle. Okay, so we'll talk about all that stuff, but basically there needs to be a way, if you're opening it up to larger angles, to get everyone on the same page and we all agree. And that's what this whole standard position is. And basically what it is, you always start out, you're going to start from the origin. The initial ray of the angle is always going to be the positive x-axis. And now positive angles always go counterclockwise. So you're going to go around through quadrant 1 and into quadrant 2. It's going to open up this way all the time. So 100 degrees, if you just think about going straight up, the y-axis would be 90 degrees. So you're just going to kind of open it up a little bit past the 90 degree, and we just kind of estimate. This is not perfect, but the key is you need to know you're ending up in quadrant 2, because again, a 90 degree angle would be straight up there. A 180 degree angle would be the other part of the x-axis, and then down the y-axis would be 270 degrees. So as long as you draw this in the correct quadrant, that's really all that matters, and get it kind of close. You want it to be closer to the 90 than to the 180. But these sketches are generally for your own use, and they're going to be useful, but they don't have to be perfect, is my point. Okay, if we want to do a negative 210 degrees, again, it always starts here. Now, instead of going counterclockwise, since the angle is negative, we're going to go around this way. So this would be negative 90, negative 180. So we need to go a little more. We would need to go about there. Okay, and that angle there would be a negative 210 degrees. Now, if you notice, it does end up in the same quadrant. It ended up in quadrant 2. So the negative 210 is actually what we drew this way. But there's another way to think of it. You know, think about how much would it be as a positive angle. And it might be easier to think about it if the full circle is 360 degrees. If you went 210 in the negative direction, that would actually be the same as going a positive 150 degrees, because those, 150 plus the 210 would get you 360. So that's kind of a way to think about it, what you can actually do. This is going to come up later, but you could start with the negative 210. If you add 360 degrees to it, you get a positive 150, and that's actually called a coterminal angle. And a lot of times it's actually easier to deal with those instead of having to worry about negative angles. And we'll talk about that in a second again, but it's just really adding or subtracting full circles, because you're going to end up in the same spot anyways. Okay, so more on that in a little bit. Next thing here, let's do one thing. Let's extend it. What if we go past 360 degrees? What would a 400 degree angle look like? How can we handle that? So the idea is, again, we start out every single time. You're going to start out positive x-axis, right? Boom, boom. Now a full circle would be 360, but we need to go 40 more than that. Okay, so that little piece there, I went 40 degrees past a full circle, right? Because I went the full 360. So what you can do, again, like I said, you can add or subtract multiples of 360, and that's going to get you a coterminal angle. So a 400 degree angle and a 40 degree angle are called coterminal again. They end up in the same spot. There's really no difference when you draw them, because really the only important part is where the angle starts and where it ends. Okay, so that is a 400 degree angle, but it looks just like, right? It terminates in the same spot as a 40 degree angle. So it will have all the same properties once we get into those later. It's just a matter of, did you do a full circle first or not? Okay. All right, but at this point, just make sure we're comfortable how to draw it. Where does it end up? We need to know it ends up in the first quadrant, that kind of thing. Okay, so here's a biggie. All right, so radians, if you remember on your calculator, there's the two different modes for angle measures. Degrees are what we kind of use, up through this point, but radians actually get used a lot more in pre-calc, calculus, and beyond. And basically, again, it's just another unit to measure angles. That's all a radian is. But it actually ties back into the circle and whatnot. Now, it is not the same as the radius of the circle, but it is related. Okay, so here's the deal. So let me think about this. Let me give you the definition, and then we will visualize it here. So 1 radian is the angle formed when the arc length, okay, we'll talk about what that is equal to the radius of the circle. Okay, so let me visualize this, or help you guys visualize this. Okay, so arc length is basically a section of a circle. So if I were to start here and I were to start tracing, let's see, if I stopped maybe about there roughly, okay, I'm just estimating. So does that yellow curved piece, if we could straighten it out and measure it, would it equal or be close to the radius of the circle, from the center to the edge there? And it looks fairly close, right? So there's an angle formed when we do that, right? So there's an angle right there. That angle, okay, if that arc length, if the yellow arc length equaled the length of the radius, if they were exactly the same, that angle would equal 1 radian. Okay, so if you think about in degrees, that angle, it's around 60 degrees. We'll see exactly what it is. It's actually a little less than 60 degrees. But that is the visualization. That is what 1 radian actually equals. So the whole point in this, or the kind of the tie-in to some old stuff, if I were to do that again, let me think, if I went to about there, right? And I were to measure this green angle, right? Okay, so that green angle. The green angle, again, measuring from the x-axis all the way there, that would be 2 radians. Okay, if that arc length, the yellow part plus the green part, that angle would be about 2 radians, depending on how accurate I drew it. Okay, and if I do it one more time, let's do another radius, it would end up being about there or so. Okay, so that angle, the red angle, right, from the x-axis all the way to there, that would be about 3 radians, right? Okay, so again, it's a lot different than degrees, right? A 3-degree angle is really, really, really small, okay? But 3 radians, I mean, that's almost all the way to 180 degrees there. So my question to you guys, okay, I'm gonna see if you're with me. How many radians do you think it would take to get to that 180 degree mark? Okay, and if you think about, is there a number, right? We can kind of visualize it's a little bigger than 3. Okay, is there any special number that comes to mind? Thinking about circles, a number that's a little bigger than 3. And there actually is, okay? The number, hopefully you're thinking of, pi, okay? And that is the case. 180 degrees actually is the exact same as pi radians, okay? So let me kind of get this on here again. So this first angle would be 1 radian. The second one, that green one there, would be 2 radians. Just abbreviate here. The red one there, that angle is about 3 radians. Okay, so the key, and this is big, okay, 180 degrees, right, just a little past 3, is actually going to be pi radians. Okay, so this whole converting to pi and using pi's and stuff, if you see pi in an angle measure, it's pretty much guaranteed to be radian measure. Okay, so if we think about, let's go all the way around, let's fill in some of these. So 0 degrees, if it's 0 degrees, it's going to be 0 radians as well. Okay, now if 180 degrees, right, so again, visualize this angle from there, we always start there, that was standard position, to there, that is pi radians, okay, 180 degrees. What would 90 degrees be? Okay, if 180 is a full pi, 90 is a half of pi, right? And we write it as a fraction, it's pi over 2. Okay, so 90 is pi over 2. 180 is a full pi. 270 is another half, right? So it's like the full pi plus another half. So it's 1.5 pi, and we generally write that instead of 1.5, we do it as 3 pi over 2. Okay, because 3 over 2 is 1.5. And then by the time you get to the full circle, if you do the full 360, you're back at 0. But that is equivalent to, if 180 is 1 pi, right, 360 is going to be 2 pi. Okay, so 2 pi is 360. The big one, though, the thing that we're going to use, because one thing we're going to want to do is convert back and forth, right? There's going to be times when they give you an angle and you need to draw it, and you're going to be like, man, I like degrees much better. We're going to use the 180 degrees equals pi radians as a conversion factor, and we're going to be able to convert back and forth. And that's probably the biggest thing from today's section. One is understanding what a radian is, okay, and 2 is how to convert. So again, just real quick, what a radian is again an angle formed. Let's say there's an angle formed right here. Okay, when that arc length, right, the section of the circle is the same length as the radius of the circle, that's the angle that is equal to 1 radian. And as that continues, 2 radians, 3 radians, a little bit more than 3, that's when you get to the pi radians. Okay? All right, so let's do some conversion. And again, the idea is use the conversion factor. It's just like anything else, in chemistry or whatever. If you convert from feet to miles or, whatever you're doing, you kind of multiply by a conversion factor. So we're going to do the exact same thing. So let's think about if we know, or we want to take 300 degrees, I should say. And when you multiply by a conversion factor, you multiply by a fraction, right? And in a fraction, if the top and bottom are equal to each other, It's really like multiplying by 1. Okay, so what we're going to do is think about, here's our conversion factor. You want the degree unit to cancel out, right? Because we want to end up in radians. We don't want to end up in degrees. We're converting into radians. So I want to put the pi radians up top, the 180 degrees on the bottom, because again, think about, just like again in chemistry or whatever, you want that unit to cancel out. And it's going to do the same thing. So all we're going to do, we're going to multiply. It's going to be 300 pi. Okay, you can put a 1 under there if you want to. It's going to be 300 pi. And then the bottom is 180. Okay, now we don't leave it like that. And one thing that's tempting too is to just throw this in a calculator and get some decimal. Okay, and it's okay, but it's usually not the way we do it. What we do, or what we need to do, you want to actually reduce this fraction. Okay, and then just leave the pi alone as pi. We don't even use the 3.14, we just leave it as a pi. So 300 over 180, if you reduce, right, you can divide both by 10 to make it 30 over 18. And then you can divide those both by 6, okay? Or similarly, you could have divided by 60 to begin with. What you can do, if you want to, on your calculators, if you have the graphing calculators, you can put in the 300 over 180. And then if you press the math button, there's the option to convert it to a fraction, and it will reduce it for you. Okay, but you somehow need to reduce this down to become 5. I'm just going to leave the pi in. But the 300 over 180 reduces to 5 over 3, right? If you divide them both by 60, that's what you get. You divide 300 by 60, you get 5. Divide 180 by 60, you get 3. And just kind of throw the pi back in. Okay, so 5 pi over 3 is going to be the way we need to write this. Okay, and you'll get used to it. There's certain ones that kind of show up, and you know, there's common ones. It's not going to be all this crazy stuff all the time. Okay, but let's do one the other direction. Let's take one in radians, like negative 2 pi over 3, and let's say we want to convert it into degrees. Okay, so to do that, we're going to multiply by the same conversion factor, but we're going to do the reciprocal, because we want to end up in degrees. So I need the 180 degrees in the numerator. I need the pi radians in the denominator to cancel. Okay, so in this case, it kind of is just a calculator problem. First thing though, notice, actually very first thing, I'm going to ignore that 2. I'm sorry, I'm going to ignore the negative sign and just kind of throw it in at the end, just personal preference. But the pi's cancel out. Okay, we have a negative. So in the numerator, it's 2 times 180, right? That's 360. In the denominator, we have a 3. Okay, and 360 divided by 3 is 120. So our final answer is we converted. Okay, negative 2 pi over 3 is equal to negative 120 degrees. Okay, so in that case, you know, one other way to think about doing it that direction, when you start out with negative 2 pi over 3, if you want to, it may be quicker. Just think about, again, what did we say pi radians equaled? Equals 180, right? So just instead of writing the pi, put the 180 right there. Right? Pi becomes 180. And it actually ends up getting you right to the 120 that we did the same way. Okay? It's just a little quicker. You don't have to worry about necessarily the multiplying by the fraction and whatnot. If you want to do that, just simplify in, like I said, or substitute in, I should say, the pi for the 180, and you can multiply. Okay, so that's converting back and forth. Get you a little practice on that, and we will be using it to do several things down the road. Okay, and one final thing in this section, we already talked about it a little bit, but let's just do another example, finding those coterminal angles. Okay, so again, coterminal angles are angles that have the same ending side. And just, you know, visually what's happening, just so we can see it real quick. Let's say I give you a couple angles here. Okay, for example, 425 degrees. Let's find a coterminal angle to 425. And we want to find one that's positive and one that's negative. Okay, so since 425 degrees is already bigger than 360, what I'm going to want to do is subtract 360 from that. And then that's going to give me another angle, okay, of 65 degrees. Okay, and to visualize that one, if you think about a 65-degree angle, 65-degree angle is going to end up in the first quadrant, right? Right about there. It's 65 degrees. And that's equal to, if I would have done a full 360 and then done 65 more, the 425, right, ends up in the exact same spot. Okay, so 65 degrees is one answer. Now, if we need another one, we can just subtract 360 again. Okay, you just keep adding or subtracting 360 and you're going to get coterminals, as many as you need. Okay, so a negative 295 degrees, sorry, that's a little sloppy looking, but that's another one. That's coterminal. All that's saying is that's if, remember, negative angles are when you go this way. So if I went 295 that way, I would still end up in the exact same spot. Okay, all of those angles are the same. They end up in the same. 425, 65, negative 295. They all end up, they all terminate in the exact same spot. Okay, last one to do this with radians, just instead of adding or subtracting 360, if you remember 360 degrees in radians is the same as 2 pi's, right? Because 180 is 1 pi. That's the one you need to know. 180 is 1 pi. So what we're going to do, we can take the negative pi over 3. Instead of adding 360, I just need to add 2 pi. Okay, so what I need to do, you do need to get a common denominator because you're adding a fraction to a regular number, to a whole number. So 2 pi is really the same as 6 pi over 3. Right, so 6 over 3 is equal to 2. Okay, so I got the common denominator. Now if that's negative 1 pi, if I add 6, negative 1 pi plus 6 pi is 5 pi. Keep the denominator the same. There's one answer. Okay, and same thing, if I want to take the negative pi over 3, since I do need a negative answer, if I were to subtract the 2 pi, okay, 2 pi again is 6 pi over 3. If I have negative 1 pi and I take away 6 more, I now have negative 7 pi over 3. There is another angle. Okay, that is in radians. It's a negative angle. It's going to be a coterminal angle because all I did was subtract a full circle. Okay, so again, that's it. Coterminal, add or subtract full circles. Okay, it can be useful, you know, and what you might want to do, the thing you might use it the most for, let's just say I gave you 425 and you're like, all right, I'm having trouble picturing where that is. But if I give you 65 degrees, most people can kind of visualize where that is because it's within one circle. It's between 0 and 360. And that's the idea there. Getting it in the right quadrant, you know, it's going to help with some things later on. Okay, all right, so hopefully that helps. And just, again, with this stuff being all brand new, just, you know, expect it to take a little time to kind of sink in, and we will be using it in a lot of newer stuff. So just practice a little bit, go back through the examples, and let's hope that it works out well for you. With a coterminal angle, the idea is, let's say you have a regular angle that ends up, so it's always going to start here. Let's just say it ends up over here or something. And let's just say for fun that is 100 degrees. Okay. The idea with coterminal is that, what if you were to do the full 360 and then do 100 more? Okay, you're going to end up in the exact same spot. So you did the full 360, then you did 100 more. So the yellow angle is actually 460 degrees, okay, because it's 100 more than a circle. But these two angles, they both terminate right there, right? So they are coterminal angles. So the idea of how to find them, all you're going to do is you're going to add or subtract 360, okay, when you're in degrees to get these. So